we got to this multiplication table. And now we want to use projection operators. To use projection operators, we need an equation. And we have to find a matrix equation. And using Hamilton-Cayley, we find the roots of corresponding polynomials of a single variable. And then we use projection operator property, which means if it's a cubic polynomial, there are three projection operators obtained by either removing this guy or removing that guy or removing that guy. Now, the way the terms are listed in this thing, and then we'll get a quadratic polynomial of remainder, and we have to correctly normalize it so it's idempotent. So we don't get extra factors here. So we first do it for eigenvalue 3, the first eigenvalue on this list. In that case, the other two eigenvalues are -3 and -0, and normalization is use this eigenvalue minus the other one, that gives me 6. This eigenvalue that gives me 3, so I get 1/18. My third class, this means 3 reflections squared. I know what it is in the table. It's this thing. It's 3 times some of the other 2 classes, plus 3 times the third class. So everybody has a factor 3, first class, second class, and third class. So there's overall factor of 3. I get 1/6, sum over the 3 classes. And now I'm writing out what that sum is in terms of group elements. First class is just identity. Second class has 2 group elements, which is rotation by 1/3 or by 2/3. And third class has the 3 flips. So it turns out this projection operator, called 1, averages of all group elements, and you can read off the characters. So this has the form over sum over the order of the group, all group elements. So this is average over the group. And each one of them gets a character of the first representation of the corresponding group element times the group matrix. So this is a trivial case where all characters are 1. So that representation always exists. It always says this: if I average over all elements of the group or all classes, not giving any special weight to any of them, I obviously get an invariant quantity. Doesn't depend. If I multiply this matrix, it'll just rearrange everybody in this row. And that's the first representation always. Then we have 2 more eigenvalues, -3 and 0. So we have 2 other projection operators. Notice in this calculation, characters just come out as the result of calculation. I don't do any voodoo by using the cookbook recipes. No cooking. P2. So this is the eigenvalue -3. Now this one will remove this term and have these other 2 terms in it. So there will be C3 squared minus 3C. And that works out to be, when you replace C squared by its values here, it works out to be first class plus second class operator minus third one. They all had 3's in front of them, so that got cancelled. And if I write them out in terms of group elements, these two graces, but the flips get a minus sign. Flips are like mirrors, a thing that used to be ordered some way, get order reverse. That's what this minus means. And this is another irreducible representation. And the characters now in this sums are either plus or minus 1. Their minus is only for the flips, but plus is for the rest. And finally, I have to do the third one. And this is superscript. This is a label for the representation, not the power of the, these are idempotent, so powers wouldn't mean anything. What happens in this case is divided by 3. And this is 2 times I. Identity representation minus the 2 rotations and no flips. This representation is kind of not obvious to me. It doesn't depend on flips. It's orthogonal by construction, so it's an irreducible space. It's good space, but it's not too obvious. Next thing we can do, we can look at spectral decomposition. Because remember, when we have an operator, then its value on irreducible subspaces is its eigenvalue. And for C1, we really just get completeness relation because C1 is the sum of these guys. Basically, you can see it, when you add 1 and 2, the third class cancels. We have to have a resolution of unity, right? So we know that by completeness, sum of projection and operator, so that algebra I should check out. Now the second operator, we did the third one already. The second one, these are rotations. And for rotations, I get these 2 eigenvalues. Well, for the third one, we just did this. We found that there was eigenvalue 3 on the first space. That's how we constructed it. Minus eigenvalue minus 3 on the second space. And then there was a 0 eigenvalue on the third space. So that's spectral decomposition of this operator. What this is doing is what the unitary character tables are doing. They're saying my classes are defined in the group element space, but I really care about irreducible subspaces. So I can go from classes to irreducible as idempotent using their eigenvalues. So this is a conversion from class space. Instead of using characters, we've used projection operators or characteristic equation and obtained the same result. So these are, 2 ways of getting irreducible representations. One is average over the group weight by characters, and look in the cookbook and use somebody's character table. The other one is I'm given some problem. I don't know anything, but I know that I should be able to construct projection operators because I have I have a prescription how to get commuting invariants, and from them construct the results. So one thing I should be able to do, I should be able to compute the dimensions of invariant subspaces from this. And for that, I can use regular representation. You know, this equation is true for anything, any representation. You might be in 27,000 dimensions. But if I use a regular representation of the group, then I have a rule that the trace of every group element is 0 except for the identity. So I see that dimension what Dresselhaus call L of the first representation should be the trace of projection operator, because remember that's supposed to produce a little block there. Trace of unity of 6 by 6 matrix is 6, so I get 1 for the dimension. Here I also get the same thing, lambda 2. Trace of everybody here except the first one is 0. This is 6 over 6. So the first two representations, which kind of always exist for all groups, more or less, suddenly the first one is always there.
What's the reasoning? All other elements having a trace 0?
Use as an example regular representation. You know, if you use some other representation, I would have to check.
Oh, okay.
But test case R is a matrix regular representation of abstract group element. That's what this matrix means, right?
Okay.
So in that case, I can verify that the first two representations are one-dimensional. So if I look at this guy, P3, in the regular representation, then trace of this is 0, trace of this is 0. So I get 2 times 6 divided by 3. And this is 4-dimensional. So what's going on? We haven't done a full reduction yet. We had 3 classes, and we've used this class to reduce the space. But we have to make sure that when I look at this class, projection operators, I have to make sure that they don't reduce what I get into smaller pieces. And indeed, that's what will happen here. I have to use all the weaponry I have. The first class is kind of trivial, it's identity. So identity is not going to simplify anything, right? But now I have to compute projection operators both for the second and third class. And it's they that will produce maximally reduced space, and there'll be nothing else that I can do. So what I'll do now is I'll go and work out kind of, you know, straightforward numerical exercise engineering style, just to, you know, give you a feeling why is it that the next projection operator produces smaller invariant subspaces, next commuting one. We are using the property that for regular representation, the only non-vanishing trace is identity. Because remember, in regular representation is a permutation matrix representation. So it's a matrix that has a 0 every place except 1 in each column and each row. So when you multiply initial state by such a matrix, it just permutes the elements. And that's what regular representation was. It came from rearrangement theorem because we extracted it from multiplication table for the group elements. So consequence of that was that when you replace these by regular representation, in this case 6 by 6 matrices, this one has ones on diagonal, but no other ones have one on a diagonal. Because rotation, just moves everybody by one step, so that's obviously off diagonal, because when you multiply some matrix, if you had something on diagonal, it wouldn't move, but that's not allowed. Everybody has to march on. And same thing is true of the flips. If you reverse the order of some elements by flipping a triangle, that also is a permutation of the group elements. So then that's very simple. Now, if you have some other representation of the group, you have some Hamiltonian and it's some size. So it's some, 12 by 12 matrix, God knows what. Then you might have to work a little bit harder to get all these traces right and all these powers right. Using regular representation as an example of this invariant space, I get trace of identity, which is 6 by 6 matrix. So that is 6 over 6. That's this one. Again, trace of identity, 6 by 6. But the last projection operator had a, 2 times identity, first class, minus something off that thing. So it was, when I took a trace, it was 2 times 6 divided by 3, which is 4. So it says that we had 6 by 6 dimensional space. We had 6 by 6 dimensional space. And it got divided into a little block, which was 1 by 1, 1 by 1, and then there is a block which is size 4. So, that's a perfectly good reduction of 6-dimensional space, but it's not full reduction. To get a full reduction, we now have to use the other set of projection operators associated with the other eigenvalue. I don't feel like doing it, but it's...
So what that means is the trace of the projection operators depends on what rep you're using.
Yeah. So, if I was in 27 dimensions, I might get the first representation, this total average, it's always one-dimensional, it's always one-dimensional.
Mm-hmm.
Doesn't matter what representation I start with, because that's just one number. So you typically get few, one-dimensional representations, then you get the rest, which is, some block. Now, the full reducibility theorem, which we proved last time and time before last, I guess, both times, is that we know that when we are done, we will get only reducible representations, but they might happen some number of times in this calculation. So character orthogonality formula is a very elegant way of stating this, and it's clumsier doing it. I mean, it can all be done in terms of projection operators. The book does it. But in computations, I often find projection operators more useful just to implement stuff. So, there are 2 parallel tracks to the same full reducibility.
In the case of D3, when we used the third class to identify the subspaces, we got 1, 1, and 4 as the dimension. So the 4 can further be reduced. It's
done well in the books. I didn't feel like doing it. When we're doing the D3 case, we had 2 equations, and you can derive them for C3 satisfies its own Hamilton-Cayley equation, which is this one. And C2 similarly satisfies an equation.
Right.
And then when you use both of them, you get the full reducibility, meaning that the second guy will split this into two invariant subspaces.
So we should be looking for what C2 does to the third projection operator of C3.
Yeah, to higher dimensional spaces, because once you've gotten to one-dimensional spaces, then all observables just return a number on it, right? That's kind of obvious.
Right. Okay.
When you have a set of commuting observables, and it's a maximal set, you cannot have more than 3. That's proven in the text of this chapter for this example, or in general, the number equals number of classes. So you cannot have more detailed splitting of the space. Then you just go through it, and there are two ways. One is you learn your characters, and you use full reducibility in terms of counting how many times representation irrep shows up in your particular problem. So that's very nice, it works well. You can always do this, and you can ignore the projection operators if you don't like them. Or you can construct equations for projection operators. Each one of them, each class invariant. And then that's the maximal resolution you can get of the space into reducer representation. So it does the same job. Projection operators are very explicit. If you have some explicit problem, I have a Hamiltonian, I have a set of coordinates, you can do explicit calculations and you get pretty explicit answer. And sometimes that's convenient. For example, you usually don't know when you have a triangle, what does this two-dimensional space mean? It says, I can reduce it to two-dimensional reducible subspaces, and I cannot split them to smaller bits. But what happens in these subspaces? What do they mean? The projection operator construction I find more intuitive. Look at the space as explained in the book, and it means that I have some kind of vibrational, stretching motion that is one of their, eigenmodes, and they have the same energy, but together they cover all possible motions in the subspace. And they tend to be intuitive. They could be standing modes or running modes, or you get some geometrical picture.